The standard procedure for an equilibrium calculation problem is to set up an ice table and use the concept of equilibrium constant to set up an equation. Let's read the problem from the beginning. Without detailed equilibrium calculations, estimate the equilibrium concentration of sulfur trioxide when a mixture of 0.160 mole of sulfur dioxide and 0.080 mole of oxygen in a 250 milliliter flask at 300 degrees Celsius combine to form sulfur trioxide. This is the chemical equation. It has two reactants and one product. When we create the ice table, we need to create a column for every reactant and every product. Since we have two reactants and one product, we need to create 3 columns. And we are provided the moles, not the molarity. Therefore, we need to create 4 rows for the ice table. This is the ice table created for this problem. Initial moles, change in moles, equilibrium moles, and equilibrium concentration. Let's fill the table with the numbers provided. Now we need to figure out the change of the reactants and the product. We have 0 product. Therefore, the reaction quotient is equal to 0. The reaction quotient must be smaller than the equilibrium constant Kc. If the reaction quotient is smaller than the equilibrium constant, the reaction will go towards the product. The concentration or the moles of the product should increase. The coefficient of the product is 2. So we will assume the change in moles of sulfur trioxide is 2x. The moles ratio between sulfur trioxide and oxygen gas is 2:1 ratio, and oxygen is a reactant. Sulfur trioxide is a product. So the change in moles of oxygen gas is negative x. Negative tells us that the moles of oxygen gas is decreasing. Similarly, the change in moles of sulfur dioxide must be negative 2x. The equilibrium moles is always equal to the sum of the initial moles and the change in moles. We can calculate the equilibrium concentration from the equilibrium moles and the volume. I put on a question mark here to indicate the equilibrium concentration of sulfur trioxide is what we are looking for. We are not looking for x. Next, we will set up an equation by using the definition of the equilibrium constant Kc. And this is the equilibrium constant expression from this balanced chemical equation. And we all know the value of Kc, which is 6.3 times 10 to the 9th power. As we can see here, this ratio is equal to a very large number, 10 to the 9th power. It tells us that either the numerator is very large or the denominator is very small. We are looking for x. We don't know how large x can go to, but we do know how small the denominator can go to. The smallest number they can get will be close to 0, but not equal to 0. So let's set them up equal to 0, say what we can get. Then we get x equal to 0.080. This is moles. We can also set this up equal to 0. We get the same answer for both x, which is good news, because we do not need to make a choice. If we do get 2 different numbers, we will pick the smaller one, because all the concentrations must be positive. We can calculate the equilibrium concentration of sulfur trioxide gas. Let's calculate. We punch these numbers into calculator, we get 0.640 molarity. At this point, you may wonder, Dr. H, when can we use the assumption that the denominator is close to 0? The criteria is that the ratio between the equilibrium constant and the larger concentration of the reactants. If the ratio is larger than 10 to the third, we can use this assumption. Let's see if we meet the requirement. We can see that the ratio between Kc and the larger concentration of the reactants is indeed larger than 10 to the third. So our assumption for this problem is valid.